Hello everyone, I'm so sorry that I can't be there on our introductory lesson. I apologise. But nevertheless, while I'm stuck in the hole with the Year 8s on their incursion, I'd like to welcome you to nuclear chemistry. Alright, well let's just jump straight into it. Today we are going to be looking at only one dot point in our syllabus. We have now moved on to section 9.2.5 and we are going to be having a look at the very first dot point. If you would like to follow along in the textbook, we are going to be covering also the content from 3.1 all the way through to 3.3. Nuclear chemistry, you will find, like our topic on galvanic cells, is quite interesting. But while we will learn about heaps of weird and wonderful things to do with radioactivity, we do need to make sure that as we progress through this chapter, we are familiar and understand and comprehend the various terminology that we will encounter. Things like mass number, atomic number, isotopes, radioactivity, and half-life. To do well in this chapter, you must thoroughly understand all of these concepts. The history of nuclear chemistry is actually quite interesting, and funnily enough centers around France. There were two quite famous French scientists of the time. The first one, labelled in your textbook, a French physicist, Becquerel, discovered that uranium compounds have the effect of darkening photographic plates or paper, even though they are protected by various other substances like just casual opaque paper. Another scientist you may have heard of, Marie Curie, who unfortunately died from radiation, discovered a compound called radium, and people used this all the time in stuff like candy, toothpaste, and even some rudimentary medicinal health tonics. One man, in fact, drank 1,400 bottles of it before his jaw fell completely off. Other interesting facts about nuclear chemistry, stuff like the Manhattan Project. That was the institution that was behind the creation of the atomic bomb. They secretly tested a lot of the effects of radiation on its own citizens without telling them, including injecting pregnant women with radioactive mixtures and feeding children radioactive oatmeal. And of course, you will all be aware of the variety of comic book heroes that like to portray the use of radioactivity as the source of all of their wonderful and amazing powers, all of which is wildly inaccurate. Now, some elements are just naturally radioactive, like radium, polonium, and thorium. But not all of them are naturally radioactive, and in fact, only their isotopes are radioactive. But what is an isotope? Well, an isotope is simply an atom of the same element that differs by the number of neutrons in their nuclei. For example, if you have a look at your textbook on page 75, you'll notice the symbol in the middle of the page, which looks like a capital M and the letters A and Z listed next to it. Now, A represents the mass number of the element, whereas Z refers to the atomic number. The atomic number, of course, being how many protons are inside the nucleus, and the mass number being how many protons plus neutrons. If we were to take an example of copper, for instance, an isotope, you'll notice, has the exact same atomic number, which in this case is 29, whereas the mass number will change. This is illustrating the difference in neutrons inside the nucleus. So what does this have to do with radioactivity? Well, while some elements, all of their isotopes are radioactive, for some, only one or two are radioactive. And so thusly, we must use the correct terminology. Instead of just using the term isotopes to refer to a type of element or subset of elements that are radioactive, we use the term radioactive isotopes. On top of that, because the radioactive emissions are coming from the nucleus of the isotope, scientists talk about unstable nuclei, which are the ones that are radioactive, and stable nuclei, which are the ones that are not reactive. So how do we know? By simply looking at the mass number of an isotope, whether or not it is going to be a stable or unstable isotope, radioactive or non-radioactive. If you have a look at this graph, you'll notice that if we plot the number of protons versus the number of neutrons of all known stable isotopes, an interesting pattern arises. For all elements that have an atomic number less than 20, the ratio of neutrons to protons is exactly 1.0. So if we looked at the nucleus, we'd expect to find the same number of protons to neutrons. This changes though as we increase up the periodic table. As soon as we hit an element of atomic number greater than 50, the ratio increases to 1.3. For elements with atomic number greater than 80, it increases again to 1.5. However, as soon as we get to elements with an atomic number greater than 83, we cannot find any more stable isotopes of that element. So atomic number 83, which in this case is bismuth, at this stage, there are no stable isotopes. So, in summary, we say that an isotope is unstable if its atomic number is greater than 83, or if the ratio of neutrons to protons places it outside the zone of stability that we looked at in figure 3.1. Well, what happens if we do find an unstable isotope? You'll find out tomorrow in our next lesson.